So we've pretty much built most of our CPU, and the microcode has been programmed with a few different instructions. So there's a LoadA instruction, which will load the contents of memory into the A register. There's an add instruction, which will add something from memory to the contents of the A register and then put that result in the A register. We also have a subtract command, which is very similar. And then there's the output instruction, which will take the contents of the A register and output it to the display. And finally, we've got a halt instruction, which will just halt the clock when we're done executing our program. In this video, I want to add some new instructions to the instruction set for our CPU so that we can use the CPU to write more interesting or more complex programs. So as we saw in the last video, we're using an Arduino to program the EEPROMs with the microcode for the different instructions that we want our CPU to support. So we have a no operation, LoadA, add, subtract, output, and halt. So I want to add a couple commands to this. So the first command I want to add is a StoreA command. And StoreA is going to work basically like LoadA, except in the opposite direction. So this is the architecture of our CPU, and the way that LoadA works is part of the instruction is the LoadA command, right? That's the 0001 is the first 4 bits of the instruction. But then the 4 least significant bits of the instruction are the memory address that we want to load into the A register. And so what our LoadA instruction does is it puts that memory address out on the bus and then reads that into the memory address register so that the RAM is pointing at that location. Then it takes the contents of RAM and moves them onto the bus and then reads that into the A register. And so those are the commands we have here. We have instruction register out, memory address register in. So that's instruction register out, memory address register in. Then in the next clock cycle, we do RAM out, A in. So RAM out, A register in. So that's how the LoadA works. StoreA is going to work basically the same way. So the StoreA command is going to be 0100. That's the 4 most significant bits that goes into our instruction decoder. But then the 4 least significant bits are going to be the address into which we want to put the contents of the A register in RAM. And so the first thing we want to do is put the instruction register, those 4 least significant bits, out on the bus. So that's instruction register out. And then read that into the memory address register, so memory address register in. So we can do that here. So that's the first part of this, is instruction register out, memory address register in. Now the next clock cycle for the StoreA command, instead of RAM out, A in, it's basically going to be the opposite. It's going to be A out, A register out, RAM in. So we want to take the contents of the A register, put it into RAM. That's just going to be A out, RAM in. And so if we compare the LoadA and the StoreA commands, they're very similar. So in both cases, the first thing we do is we point the memory address register at the appropriate address. And then for LoadA, we move the value from RAM to the A register. For StoreA, we move the value from the A register to RAM. So that's the StoreA command. That's it. The next instruction that I want to add is similar to LoadA in that it's going to put a value into the A register. But the way that the LoadA command works is it puts a value from RAM into the A register. So if we say LoadA 15, for example, as our instruction, then we're going to take the contents of RAM and put it into the A register. And another way to think of that is that's an indirect instruction, because when we say LoadA 15, we're not putting a 15 into the A register. We're first putting the 15 into the memory address register, and then we're getting the contents of address location 15 and putting that in the A register. But sometimes it's useful to just put a particular value in the A register, not from RAM, but just an immediate value. So if we say LoadA 15, we want to just put a 15 in the A register. And so I'm going to add a command to do that called load immediate. So we'll call it load immediate, LDI for load immediate. And really what we want to do is we want to take the contents of the instruction register, or at least the 4 least significant bits, because the first 4 bits are going to be the instruction itself. So for load immediate, those first 4 bits are 0101. So we're going to have that. But then the next 4 bits are going to be the value that we want to put in the A register, which means this is a very simple instruction, because after the fetch cycle, after we've fetched the instruction and it's in the instruction register, we've already got the value that we want to put in the A register right here. And if we do instruction register out, it's going to take the 4 least significant bits and put them on the bus. And then if we do A register in, then it'll read those from the bus. So that's what we'll do. We'll do instruction register out and then A register in. And that's actually all we need to do for that instruction. Everything else we can just leave at 0 and we won't do anything else, because once we put that value into the A register, we're done. That's all we want to do. Now, one interesting thing to point out with this instruction is because we're only able to put the 4 least significant bits of the instruction register into the A register because, well, for one, that's all we have wired up to the bus when we do instruction register out. It's only those 4 bits that go out on the bus. And also that's because the first 4 bits are the instruction itself. So for load immediate, that's going to be a 0101. That's always going to be what that is. So what this means is that when we do a load immediate, we can only load a value from 0 to 15 into the A register. We can't load, so if we wanted to load immediate, 52, we couldn't do that because we can't represent 52 in 4 bits. So you might think, well, this is maybe not the most useful instruction, and perhaps in some cases it's not. Some cases you might need to just put that 52 in RAM and use a load A. But I think it's still a useful instruction to have because a lot of times in a program you'll want to initialize the A register to 0 or to 1 or something like that, and this load immediate instruction will let us do that. And the last instruction that I want to add today is a jump instruction. And the jump instruction is extremely useful because all the programs we've run so far, we've started at address 0, we've executed through the program, and at some point we get to the end of the program and we use the halt command to halt the program, and that's it. A jump instruction is going to let us add loops to our program so that we can run a program in a loop that runs over and over again. And the way it's going to work is by updating the program counter. Because remember, at the beginning of every instruction, when we load the next instruction to execute, we're loading it from RAM, but the address that we go to is whatever is in the program counter. So if we look at all of our instructions, they start out with memory address register in counter out. And of course, counter out is the program counter, so that goes out into the memory address register. And then the second clock cycle of every instruction is RAM out, instruction register in, and counter enable. So RAM out, instruction register in, that's fetching that instruction from RAM, putting it in the instruction register, and then we go ahead and execute it in the following clock cycles, and then increment the program counter. So if the first instruction of our program is 0, then we increment this to 1, so that when we're done with the first instruction, then we load the 1 into the memory address register and fetch instruction 1. And then we increment this to 2, so that the next time around we'll fetch instruction 2. But you'll notice that for all of these commands, we're doing that counter enable, which increments the program counter here at the beginning of the instruction, so during the fetch cycle. Then we execute whatever steps are appropriate for that particular instruction that we've loaded. Which means at this point, if we change what's in the program counter, then when we finish executing that instruction and want to go on to the next instruction is going to be whatever is going to be fetched from whatever address is in the program counter. So in order to do a jump, which is basically just changing the program counter, all we need to do is take the address we want to jump to, which is going to be part of our instruction, it's going to be the 4 least significant bits of our instruction, put that on the bus, read that into the program counter, which is a program counter in, or the jump signal, and that'll update the program counter so that when we finish that instruction, the next instruction we execute will be the instruction that we jumped to, not just the next one in memory. So again, this is a very simple instruction to write the microcode for, because we're going to take the instruction register out and then set the jump bit, which is essentially a program counter in. And that'll put the address that we want to jump to in the program counter, and we don't need to do anything else. So let's go ahead and reprogram our microcode EEPROMs with this new microcode that has these new instructions. I'll pull these out, put them into our Arduino EEPROM programmer, and then I'll go ahead and upload this new code. Look at the serial monitor. And there we go, that's the first one. And now I'll program the second EEPROM, and I don't need to re-upload the code, I can just reset the Arduino. And there it goes, programming the second one. And we're done. So I'll take these EEPROMs and put them back in our computer, hopefully in the right place, and let's give it a try. So let's try writing a program that uses these new instructions. So I'm going to write something fairly simple that just puts a 0 in the A register, and then adds 3 to that and outputs the result, and then does that in a loop. So basically what I want to do is just output all of the multiples of 3. So to start out, we want to start with a 0 in the A register, and we might be able to assume that this is going to start out as 0, but it'd be a good practice to initialize it to 0, and we can do that by using our load immediate command. So if we say load immediate 0, then that's going to put a 0 in the A register. Now next we want to add 3 each time we go through this to the result. And we don't have an add immediate. I'm not sure that would be that useful a command, although I suppose you could add something like that. But without anything like that, when we use the add command, we're going to refer to a memory location. So if we say add 15, then this is going to add the contents of memory location 15 to the A register, which we just loaded with a 0. So if there's a 3 in location 15, then we'll add a 3 to that load immediate. And then we want to output the result. And then we want to jump back to our add command and just go in a loop here. But what we can do, instead of pre-populating this address location 15 with a 3, we can also load that into that location ahead of time in our program. So what we could do is we could do a load immediate 3, which puts a 3 in the A register, and then we could store the contents of the A register using the StoreA command into location 15. So the load immediate 3, StoreA 15, will put a 3 into address 15. Then we're going to load a 0 into the A register and then add the contents of 15 to it. So we're going to add 3 and output the result. So this is going to output a 3. Then if we do a jump and we just jump back to this add command, then that's going to add another 3 and output the result, and then add another 3 and output the result, and that'll do what we want. It'll output each of the multiples of 3. And so to figure out what we need to say here for our jump command, we need to know what address we want to jump to. So if our program starts here, this is going to be address 0, this will be address 1, address 2, address 3, address 4, address 5. So our whole program is going to be 6 bytes long, 0 through 5, and then we want to jump back to address 3. So we say jump 3, then that'll load a 3 in the program counter, and the next command we execute will be the add 15 again, and then the output, and then we jump 3. It'll, when we start the jump 3 command, it'll increment the program counter from 5 to 6, because normally we want to go on to instruction 6, but then during the jump command, we'll rewrite the program counter to 3, so that when we finish this command, the next command we execute will be from address 3, and we'll do the add again. And so this will just continuously loop and output all of the multiples of 3. So this is the assembly language for our program that we want to write. Now we need to convert that to the machine code, or the byte code that we're actually going to program into the computer. So the first thing I'll do is take the addresses, because we need to know what address we're putting this in, and write those out in binary. So these are the addresses. And now for the instructions, we need to look up each of the opcodes in our microcode. And so if we come over here, we can see that load immediate is 0101. So that'll be the instruction for that, 0101. And then we're doing load immediate 3, so the operand here is 0011, which is 3. So the next command is StoreA. And so StoreA is 0100. So 0100. And we're going to store A 15, so address 15. So we're storing that 3 in address location 15. Then the next command is load immediate 0. Well, load immediate is 0101. We already know that. That's what we used here. And we're loading immediate 0. So we're putting a 0 into the A register. So there's our 0. The next command is add 15. So add, if we look at how we programmed our microcode, add is 0010. 0010. So that's the machine code representation of the add assembly language command. And then 15 is 1111. And then output is 1110. So 1110. And output doesn't take any parameters or anything like that. So we could put anything we want here. So we'll just put all zeros. Doesn't really matter though. There's no part of the output command that actually looks at that. And then finally jump 3. So the jump command is 0110. So 0110, and then we want to jump to address 3. So 0011 is 3. So this is assembled binary machine language for this program. So let's give this a try. We'll power up the computer, stop the clock, reset everything, and go into programming mode. And I'll go ahead and enter the program into the computer 1 byte at a time, and I'll speed this part up so you don't have to wait for me to toggle in every byte. Okay, and that's it. And now I think I've got the whole thing programmed in correctly. So we'll go back into run mode, and let's step through it and see how this works. So the first command is load immediate 3, and so we'll fetch that command. So we have our load immediate here, 0101, and then 3. And the way load immediate works is it just takes that 3 and puts it in the A register. So we have instruction register out, A in. And there we go, we put the 3 in the A register. And then the next 2 cycles, we don't do anything. Now we move on to our StoreA 15. So program counter's at 1. So we're going to fetch from address 1, put that in the instruction register. And so StoreA 15, we've got our StoreA and our 15 here. So we take this 15, put it in our memory address register. So now we're pointing at address 15. And of course, right now there's just junk in that memory location for whatever happened to be there when we power the computer up. But we want to take the contents of A and put it there. So we have A out and RAM in. So that should take the contents of A and write it into memory. So now we've stored that 3 in memory at location 15. So next thing we're going to do is another load immediate. So we'll fetch from address 2, and here we go, address 2, and we'll fetch that. And so now we have our load immediate 0 in our instruction register, which means we're just going to put that 0 into the A register. So there we go, we've initialized our A register with a 0, and now we want to start counting by 3s. So we want to add the contents of location 15, which has a 3 in it. So we're going to add 15. So add, we're going to fetch that. And of course we're at address 3, right? So program counter's 3. So we're going to go fetch the contents of 3, put that in the instruction register. So we have our 0010, which is the add opcode, and then 15. So if we look in address 15, we put that into our memory address register, we've got the 3 there. And we want to add the 3 to the 0 that's in the A register. So we put the 3 in the B register, and then we take the sum and put that in the A register. And so that's our add 15, so that's added the 3 there. And then we want to output that result. So we fetch the next command, which is our output, and we output the result. So there's a 3. Now we're going to move on to the jump command. And so our program counter is pointed to address 5, so that we're going to execute from address 5. So we're going to fetch the instruction from register 5. So we have counter out, memory address register in. So program counter out is going to go into our memory address register. So now we're looking at the contents of memory location 5, which is our jump command. So 0110, and then the 0011 for the 3. So we'll put that into our instruction register. And you'll notice that we've also incremented our program counter. And so the program counter is now pointing at 6, because normally we'd want to execute instruction 6 next. Except in this case, we're not going to do that because we're doing a jump. But the program counter is incremented to 6 so that when we finish this instruction, we would naturally load the next instruction from location 6. But the way the jump works is we're going to take the contents of the instruction register, which is 3, because when we put stuff out on the bus, we only have these 4 bits hooked up. So that 3 will go out on the bus, which you see on the bus, the 3. And then we have our jump bit set down here, which means that the program counter is going to read in that 3. So instead of 6 being the next instruction we execute, it's going to be 3. And that's how the jump works. So that means the next time through, we're going to load from 3. So we've jumped back to instruction 3. And so we don't do anything else for the rest of that instruction. And so now we're back at our fetch cycle. And the first part of our fetch cycle is program counter out, memory address register in. So we're going to take our program counter 3 and put that into our memory address register. And so we're actually loading this add 15 command again. And so we'll load that into our instruction register, and then we'll go through and do our add. And so here's our 6 in the A register. And then we go ahead and output that. And so there's our output. And so if we just let this program run, it'll go ahead and loop through these last 3 commands, adding the contents of location 15, which is a 3 each time, and outputting the result. And so we see the output counting multiples of 3. And it's just going to keep doing this forever. We can speed it up, and it goes even faster, but it's still counting multiples of 3.